Burnout? Ready for vacation?
Tired.
Tired. Yeah. My first meeting started at 6:30 and then I just looked at the clock. I'm like, oh, it's 6:50. Oh no. And then dialed into class and I dialed into 172. Dialed. Yeah. It's like we're using AOL, right? I zoomed into 172 and I'm like, where is everybody? It's like, oh man, wrong class. Good times. All right. So we're at the home stretch for this whole thing. And okay. So we're going to talk a little bit more about this whole stiffness matrix equation, how that whole thing sorts out. And then kind of the final topic that we need to kind of pull all this together is the numerical integration, or it's called the numerical quadrature. And that's where we take this stuff that we've been looking at, this finite element method, and figuring out this stiffness matrix, and we break it up and discretize it in a way that you can actually solve it numerically. So that's the last step in this whole process. And that's where we get to this idea of integration points. And what the integration points are is that's where you're actually solving this differential equation. So we have this dE that we've been looking at, right? And it's basically just an integral. And I've kind of led you to believe that we're solving that problem at nodes, right? We talked about how we had an element, whether it's a line element, and we have nodes at either end, or we have a line element and we have 3 nodes. I've kind of implied that we're solving that equation. We're solving that integral at each one of those nodes, but that's actually not the case. We're solving it at intermediate points in between there, and then we have to extrapolate out to the nodes. So that's kind of the last step for this process. So I'll show you how that pulls into it. I'm just trying to figure out. Yeah, I think we're probably going to get through that actually today and tomorrow and Thursday. So just kind of looking ahead here. Yeah, it'll go pretty fast. And then I guess we should probably talk about a final. So I'll put together a final, and it's basically just going to be a take home. And if you sit down in front of your notes, it'll be, based on, the time sequence that we went through notes in class, and I'll ask you kind of qualifying questions and things like that. Like, I may ask, what is the Jacobian with regards to finite element method, very conceptual question like that. And we're actually going to answer that particular question tonight. So we'll spell that out. And I think actually in my notes, I have, this is the Jacobian. So, that's a good thing to note. If I write that down, you should note things like that. So I'll ask very conceptual things like that to make sure you know the high level of this. And then I think next week, if we have time, I'm going to show you, I'll kind of give you a live preview of a MATLAB code that I've put together for a one-dimensional finite element code. And I was gonna just send it to you guys, and then walk through it, but I'm not the 100. I didn't author 100% of the code, so it wouldn't be right for me to send it to you. It was collaborative with teammates that I had at UC Davis, so we all contributed to it. But I think it would be reasonable that I can at least kind of walk you through it, because you can see the code, you'll see the equations that we've been working on here in class. You'll see how they kind of come together numerically. And I have a simple process. And I think Jacob, you have seen this code. I think I shared it with you once before, or at least showed you results where we can compare a closed form solution result from a displacement perspective based on different number of elements. So we can say, okay, if we take this closed form solution, that gives us an exact solution. And we know what that exact solution is because we solved for it by hand. And then we say, okay, let's discretize that with 20 elements, and how close is that approximation? And let's discretize that with 100 elements, and how close is that approximation? And really, that's what we're trying to figure out, is how close of an approximation is good enough, and that's up to the end user to decide that. But the point of this class is understanding how you actually get that data. And hopefully all of you realize that all of this stuff that we're doing does not give you an exact solution. It gives you an approximate solution. Excuse me. So you don't want to be one of those folks that runs an FEA and then you're fighting tooth and nail that it's truth, because it's not exact. It's an approximation, and it's as you know, we've gone through this. I haven't counted it, but it would be interesting to count you starting at the beginning of the process of our strong form, how many places we make assumptions. And like we make an assumption for a boundary condition, we make an assumption for a weighting function, we make an assumption for a shape function. We've made all of these assumptions saying, well, if this is true, then this is true. And if, if the strong form holds, then the weak form holds. If you actually added up all those assumptions that went into it and you had any particular deviation there, that's actually quite a bit of error that you could get. And I think that's the important point that I want all of you to take away from this is, yeah, it's an approximation. And you want to make sure that you're always on the conservative side, meaning that your results are showing larger displacements than you think you would get, or leads to higher strains or higher stresses, right? Those are all kind of linear dependent. But make sure that when you're making those assumptions, you're always like, which one is going to give me the worst results? Is kind of the way that you should be thinking about it. So that way we can lead to safe products and not under design. But there's a limit to that, right? You can be so ultra conservative with that you have, airplanes would never fly, right? We'd have basically trains in the air and you wouldn't get them off the ground if we thought that way literally all the time. So I guess, you have to decide on those assumptions. Is it worthwhile to dig a little bit deeper and to refine your assumptions? That may be the case. So let's get, trying to get Microsoft open here. Okay, hopefully you're seeing a blank screen.
Yep.
Hey, we have green today instead of red for starting out of the gate. It's been red lately. Not that I have anything about green, because project managers like green, right? If it's green, it means it's done and it's good. Those of you that know me outside of class, that I have a very fond feeling for project managers. What's the date? 5-4. Okay. We need them. There's just a certain stop there. Okay, so we're talking about stiffness matrix. So we left off with a form like this. So we need to get stiffness matrix. Hey, before we get too far along, are a lot of you have a long way to go in the program, or is there anybody graduating like this semester or next semester? No?
I'm deciding to opt out and pursue a little bit like deeper program.
Okay, so you're gonna transfer to a different school?
I'm gonna take a year off to figure things out and kind of like see more of industry and figure out what I like, and then reapply into a program that's more research focused.
Ah, okay. So are you in the master's program right now, or are you undergrad taking
Yeah,
graduate courses?
I'm like that blended part where I'll graduate in a few weeks, and
Okay.
then I would enroll as a master's in fall.
Oh, okay. Very good. So you're probably leaning more towards PhD then, if you want it more research oriented.
Possibly, who knows? MEs don't really need it, right? So
I don't know. It's a good thing to have on your resume, especially if you want to do research. Well, the reason I ask is I talked to Troy recently, and I'm considered adjunct faculty. I'm part time, so I can't create a new class. It has to be under someone else that does that. So he said that he would sponsor me creating a graduate level composites class, and that would be fun.
Next semester?
No, I can't get it together by next semester. It would probably be the semester after that. But it would be a blend of, the beginning of the semester, we were talking about all those uh, stiffness matrices and things like that, or material, the C matrix and the S matrix and things like that. Some of that would be repeat. We'd go into a little bit deeper, but then we would get into the analytical methods behind all of that. So applying, how would you approach finite elements to that? It would be a mixture. And that one would be, I've talked to him a little bit more about it. That would be, you'd have to have graduate enrollment with 201 and 202. So that way we could really get into the math, and I can give you problems and do some MATLAB scripting and stuff. So that's coming up. I think I can have it ready, and not for next semester, but maybe the one after that. So that's why I was asking. I think it'll be a fun class.
yeah, it sounds pretty cool.
So if you're still around, watch for it. Okay. So hopefully some of you are like, yeah, I'll stick around.
It sounds awesome, but I might transfer out before then.
Yeah, whatever. That was a joke. I'm kidding. So we have this stiffness matrix, alpha, beta to the m. So we're at the element level. Stiffness is equal to the integral. Do you already have a place in mind that you're going to transfer to?
I'm going to try Purdue, and we'll see.
Nice. Nice. So we have the integral of omega m. And we have our B matrix, B alpha to the M. So again, the M is just indicating we're at the element level, and it's the transpose of that. C, so this is just our C material matrix, or, if this was just a single element, this would be represented as an E, right? Capital E. B, our beta, B, and our differential is over a volume. And kind of just to recall this, this is a matrix. It's a 2x3 matrix, and we have this n alpha with respect to 1 and a 0, and n alpha with respect to 2, n alpha 2, and alpha 1. And remember, these n's were our shape functions, right? So kind of a reminder of where we left off with our equation. And we have two things going on here. So one, we have n alpha with respect to psi nu, but we need the partial of n alpha, the partial of n alpha regards to x. So that's one thing that we have going on. And two, how do we actually carry out the integral of omega m I'm just going to say dot 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 dv. We have this integral. Yeah, that's great. What do we do with it? How are we going to solve that? Okay. So resolving 1 and 2. Number 1, chain rule.
Hey, Professor.
Yeah.
Just for clarification, the two variables for the shape function are z and mu?
C and nu.
Nu, okay.
Yeah.
Thank you.
Okay, chain rule. To get the B matrix, B alpha M. So that's what we're trying to get. So we're going to say the partial then alpha regards to xi is equal to the partial of n alpha respect to c dc dxi plus partial of n alpha n mu dxi, where I is equal to 1 and 2. And this is going to break up into a matrix. So we're going to, these are all matrices. So we have n comma 1, n comma 2 is equal to C C1, 1, 2, And alpha C and alpha U. So you remember all the way back from the beginning of the semester, we have some matrix is equal to a matrix times a matrix, and we need to do a coordinate transformation. Remember that whole debacle that we went through? I think I gave you an example with, we have, I don't know if I gave you, was it strain in like a local or a global coordinate system, and we went through this whole transformation deal to go to the other coordinate system, going from local to global or global to local. Remember that whole thing where we created those relationships and walked through that?
Yeah.
That's kind of the same thing here. Same thing. So this is what we have. We have this guy. We need this one. And we want this. This is yeah, so we want, let's just write that. We want that. So we want this guy, we need this, and we have this. So we can say that actually, I'm gonna write this in. V alpha M is what we want. This is actually J I think it's minus T. I think this is the inverse transpose IT. It's kind of a not important point. So we can get this thing where we have x1 respect to psi. And remember, this means partial derivative, right? We talked about this a long time ago also, this notation. And this is x2 psi, x1, x2. So do you guys remember this notation of what this was? This partial derivative, like just take this x1. Wasn't this the partial of x1 with regards to psi? Does that sound familiar?
Yeah.
Okay, so these are partial derivatives, right? These are partial derivatives relating our x coordinate system to our z coordinate system. And remember, so we don't lose track of where we are, we're talking about an element, and this is x1, x2, and we're mapping to C1, C2. So this would be like C1 right here. I guess I've left that subscript out. So we're mapping, remember? Back and forth. So taking this partial derivative is part of this mapping. That's still what we're talking about, and that's still what's going on. We're going from node to node, element to element. We're doing this this mapping, and so this equation right here, or this partial derivative matrix is the Jacobian. This is the Jacobian. And in finite element terms, when we're talking about finite elements, the Jacobian is just a matrix full of our partial derivatives relating our global coordinate system element to our local coordinate system element, so we can actually go through and start doing our computations.
So where's the Jacobian in the equation above? Is it not there and we're going to use it on that equation?
Well, this one's a little bit different. This is the transpose of it. So this is C comma 1. So C comma 1, it's actually C1 comma 1. This is equal to the partial C1 regards to X1.
Oh,
So-
okay. That makes more sense. I didn't.
Yep.
Yeah.
Yeah.
It almost looked
let-
like the partial derivative stuff, but then I only saw a comma 1.
Yeah, let me rewrite this so you guys aren't confused. So it's the inverse transpose of what we'll be referring to as the Jacobian. C1 comma 1. So it's 1 comma 2. And oops. 1 comma. Okay, so Jacobian is partial derivatives, and it's related to our mapping. And in this particular case, this is the Jacobian of the isoparametric transformation. I should have written that up higher. Okay, I'm gonna rewrite this. We'll say where xi is equal to the sum of alpha equals 1 to 4 xi alpha and alpha c n. And note that the partial of c with respect to c is equal to 1. Oh, okay. Which is equal to c comma 1 times x1 comma c plus c comma 2 x2 comma c. So I made an error. I think it was I was wrong to correct this, Jacob. I thought it seemed odd when I was correcting it. These are comma 1, comma 1, comma 1, comma 2, comma 2, because the partial of c with regards to c is equal to 1, and that is equal to this c comma 1. So c comma 1 is equal to 1. So this is 1 times this is equal to 1 times the partial of x1 regards to c plus the rest of this. So it would be 2x partial of x2 c. Because Can you guys write the C? C, or at least on the screen you can. X1 C new comma X2 C. There's more to this. So I have a few of these here. So to repeat, we have the partial of C respect to C is equal to 1. And again, C comma 1 X1 comma C plus C comma 2 X2 comma C. This was, sorry to repeat this one, but it's carried over to another page and I have a whole bunch of things together. We have the partial of C with respect to nu is equal to 0. And this is equal to C comma 1 X1 nu plus C 2 X2 nu partial of nu with respect to C is equal to 0, which is equal to nu comma 1 X1 comma C plus nu comma 2 X2 comma C. We got 4 of them there? No, I have one more. The partial of nu respect to nu is equal to 1, which is equal to nu comma 1 X1 comma nu 2 X2 nu. So now we get 1 0 0 1 is equal to C comma 1 C comma 2 nu comma 2 nu comma 2 times X1 comma C X1 comma nu X2 comma C X2 comma nu. You guys see where this is coming from these 4 equations? Where, as a reminder, C comma 1 C comma 2. This is our inverse transpose Jacobian. So we need the transpose of this. And this is the Jacobian. So 2. Now we have n alpha comma 1 and n alpha comma 2. So how do we evaluate the integral of omega m? And this is just some function f x1 comma x2 dv. Well, we map. we map alpha M back to, or sorry, omega M back to omega. And integrate that. So what the heck is going on here? We have this strong form. We throw some terms at it. We get a weak form. Okay, we have this weak form, which is based on the minimum potential and energy theorem. Okay, that's tried and proven. That's, you know, we're all fine with that. And then we go through and we apply these basis functions, right, into this problem set, and we create these elements, and we go from this global coordinate system element omega, and I'm saying, okay, now we're gonna, in order for us to do anything with this, we have this stiffness matrix that lives in that space, right? We have this started up here. We have the stiffness matrix that we've mapped into a local or it's at the elemental level, right? So we've mapped from global. So we've mapped from this global coordinate system to a local element, and we have a stiffness at that element. And now we're using these shape functions, these ends, to map over to with help of the Jacobian, to map over to this other space, this local space, this C space, right? And we went through and did that mapping so that way we could find this N alpha 1 and alpha 2. That's ultimately why we did that, what we're trying to get. So we created we have this relationship between the C and X and nu and X. And okay, great. We have this partial derivative thing matrix that you're saying is this Jacobian. And we went through that. And now I have this in alpha 1 and alpha 2. Now you're telling me I have to map back from my C space element, or from my elemental level back to my global. That's unfortunately exactly what we're going to do. So hopefully you're not royally confused, but that's why this coordinate transformation thing is important. So we're going from one space where we have some information, but we need other information. So we're going to this other space, or this other coordinate system, coordinate transformation, to figure something else out and then come back. At least at a high level, do you guys follow that? We're just using these mathematics to go from one space to another space so that we can solve for things.
So like, are you saying basically we're taking something that we don't know how to do it and putting it in a sort of, putting it into like a realm where we can understand it and analyze it, and then put it back in once we figured out
Exactly.
what we're doing? Okay.
That's exactly what we're doing. Yep. It took a very intelligent mind to figure this out. So we have this coordinate system here, and we're going to call this x1, x2, back to the days of the beginning of the semester, and we were talking about composite stuff. And we have something here, and we have this little volume right here, and we're going to say that this is a dV. So it's just a derivative of a volume, some volume. And let's say that this is our omega m. So this is our element, or this, we're in our element space, and we're in our deformed space. And then here's our undeformed element. And here's that same space over there. And in this space, this is C and this is U. This element space, it's not the differential of a volume. This is DC U. Where we can now state that dV, so the differential of our volume in our deformed state is equal to our Jacobian times our differential element in our undeformed state.
Well,
So-
in this case, since it's two-dimensional, would it be a dA instead of a dV?
Yeah, it would be. It's still just we still list it as a dV though.
Okay, just checking.
Standard notation, but yeah. In this particular case, to go from one coordinate system to another, I told you that this Jacobian is a it's a matrix, right? But in reality, the way we want to think about it is so this is the Jacobian. Think of it as a scalar that helps you map between the two spaces. You remember at the beginning of the semester, we had the M matrix? And it was a bunch of, I don't remember offhand what, it was like cosine, sine, sine squared, da 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 da. Remember that? Very roughly, it was a matrix of sines and cosines. And that's what we used in that exercise to map from a local to a global and back. We had an M matrix.
Is that our basis function?
It was our basis functions, yeah. That's exactly what the Jacobian is. And the reason they say it's a scalar is when you take these partial derivatives, you get scalars. So it's a scalar matrix, but that's what you want to think of it as. It's just a tool. And that tool isn't something that you're just going to look up out of a textbook. This tool is sharpened. It's created specifically for the problem that you're working on, because the Jacobian is, it's custom tailored for the mapping from one element to another element, right? Based on our basis functions and all that stuff. It's all intertwined, right? This is all, here's our basis function, basis n, and we're trying to figure out what that n comma 1, n comma 2 is. So it's all interrelated as far as our problem, and even more so if we have our potato, and I have some element here, and let's say I have another element over here, not that you would do this, but let's say that I have within the same volume, potato, I have, you know, a 4 element and an 8 element. Are these 2 elements going to have the same Jacobian? They won't, right? Because our Jacobian for this element here, for this 4 node one, is based on shape functions that were designed specifically for this guy. Remember, this is N1 and this is N2. This shape function will be different. It'll be, remember that? N1, N2. So if you have different element types within your body, you're going to have different Jacobians. So your calculation process that you're going to have to go through has to calculate this essentially for every element type. And specifically, it's going to do it for every element because every element is in a unique location. So you have to map from this coordinate system to this coordinate system. And then you're going to map again to this coordinate system. Oh, I guess that's not there, it's in the middle. So you map global to semi-global and then map to your C space. And then you got to map back and then map back to your global, your big global. So there's a lot of coordinate transformations that go on in this process. So you can see that different element types are going to give you different shape functions. And also element location within the body is going to give you a different sub coordinate system here. So it's going to be unique as well. So probably should have wrote this somewhere else. So to continue, so we can now state that this differential volume is equal to the Jacobian times the dCt nu. And so continuation. And the integral of omega m f x1 comma x2 dv, oops, not dx dv, is equal to the integral of omega f x1, function of c and u, comma x2, function of c and u, times the Jacobian c u d c u.
So as far as relating the x1 and x2 to the diagrams you have up above, those take you from
this is x1, this is x2 here. This would be x1 global. This would be x2 global. So this is a local coordinate system. X1, X2 is local, it's considered a global element. And then we go to a local element, which is C, new. And it's a little bit backwards because we're assuming that our deformed element is in this x1, x2 space, and that in our local element, we are undeformed. You notice that here? So this element right here, when we're in our elemental space, is in the x1, x2. And then when we map over to our C space, it's in an undeformed state. But at this point with the Jacobian, we're looking at just this particular small, just the representative small volume within the element. So we're still not talking about nodal displacements or anything like that yet.
And then there's two shape functions per node, because is it give one from what and for that 4-element one?
Yeah, there's two.
From
yeah,
the alpha node to one of the beta nodes.
Yep.
And then the other adjacent alpha
Yep.
node.
Yep.
So there would be, for that element would have 8 different shape functions then. Each node has 2 shape functions.
Correct.
For that 4 node element. Okay.
Yep. Yep.
Okay.
Okay. So we have this integral for our element, which is based in our x1, x2 domain, which is a differential of the volume. And we're creating this relationship between our element in our omega space, and this term all the way at the end is dv, and that is equal to the Jacobian. Oh, sorry. It's not equal to that. This is dv. This leads to the Jacobian, which is equal to the determinant of the Jacobian matrix. So let's talk a little bit more about this element. That was supposed to come off the arrow.
Is the Jacobian considered a transformation matrix?
It is.
Okay.
So we have new and C. We have an element here. Here. Let's write this down. I need more space. So let's say this direction is this direction is C, and this is B, C, 0, and this is 0. And we're going to do some mapping. X2, X1. So we're going to get this. So what we're talking about here is, no, don't do that. We're talking about these tiny little elements here within the body, okay? So these are one and the same. We're in our C space, we're in our x1, x2 domain. So we want to draw this one intentionally askew because we want to give the impression that it is not the same shape as this guy. The shape has changed. So this guy here is x1 comma new d new comma x2 new d new, and this guy is x1 comma c comma x2 comma c, and that one maps to there, and this one maps here. So it's a coordinate transformation there. This is dv, and dv is equal to the absolute value x1 comma c x2 comma new minus x2 comma c x1 comma new, close brackets, dc d new and I'm just going to go like this. This is the determinant of J. So dv is equal to the determinant of J dc new, and k alpha beta m is equal to the integral of omega m beta alpha transpose stiffness matrix, or material stiffness matrix, b beta m. This transpose, there's an m here, m transpose.
On the first dv equation you wrote there, the determinant includes the d c and d new.
Yeah.
Then on the second line, that looks like there's an additional d c and d new outside of the determinant of J.
Yeah, good catch. So there you go. So beta m transpose material stiffness matrix beta b m dv is equal to the integral of omega b alpha m transpose c b beta m. Let's throw in some Jacobian d c d nu, and we now know that this last term is actually the determinant of Jacobian. No, that is, yeah, dv equals Um, all right. That whole thing is yeah, that's what it is. So the difference between, so J is just a scalar. J squiggly is a matrix of scalars. So when we have the determinant of J here, we're talking about the entire matrix. So this portion here is determinant of J. So dV is equal to the determinant of J times this, just like we have written here. So we actually have to replace this dV right here with this whole thing here. So it is determinant of J dC. Okay, yeah, so we're good there. Okay. Some narrative to go with this. I can get my mouse. Keeps disappearing. Green, go away. So this integral must, as a practical matter, be approximated via numerical integration using a method referred to as numerical quadrature. So I'll kind of give you a little bit of a lead in, and then we'll get into it on Thursday. So numerical integration in one dimension first. So we have this integral -1 to 1 f c dc is approximately equal to the sum k is equal to 1 to NSP, number of sampling points, of this WK FCK, and this WK are weights. This CK are sampling point locations. And think of it as a number line, -1 to 1. And we have this FC. And let's see if I cannot butcher this. It's just a that was supposed to line up. We just have a function from -1 to 1. Yeah, that was supposed to be in the center. I'll just make the line fatter to make it in the center. So we need an integration rule. Rule. We're going to say this NSP, number of sampling points, comma, CK, comma, weight K, where K is equal to 1 to the number of, I guess that's redundant, NSP, 1 to number of NSP. So I think that's where I'll leave you hanging. And then we'll get into the excruciating details of that on Thursday. Okay. So essentially what we're going to do is we're going to create these subpoints within our element. So just generalizing here for the last minute or so. We have this two-dimensional element. And we said that we have these shape functions, right? These N1, N2 shape functions. And these shape functions are allowing us to map between X domain, X space, to this C space. But now we're going to say, well, now we need to actually perform this integration from a volume from one coordinate system to another coordinate system, and we're going to pick these subdomains. We're going to do it at these locations within the element. We're not going to do it at the nodes that are represented by these shape functions. We're going to do it at these other locations as part of our integration rule and our weighting. So we're essentially going to come up with these their weights. These points are WKs. Those are our weights of where we're going to do this integration. So we're actually going to do all of our calculations for the displacements of our component at this level, and then we're going to report out what these results are. It's not this simple, but we're going to report out what they are at the nodal value. And then if someone wants to know information about this element, you have to take the results of all of those and report out to some global reporting. But for right now, that's what we're trying to get down to, is we need to solve this integral at these intermediate locations within our element. So that's the final step to this whole process. And those of you that are interested in it, that's where we'll actually talk a little bit more about element. This is what's called element formulation. Are these shape functions in combination with these integration rules is what creates this topic of elements. Okay. All right, folks. I'll see you on Thursday.
All right, thanks. See you.